The sun is to the right of the slit.
Too far. Move back. Just a little bit. Hold it. That's it.
Perfect, George. We've been adjusting a heliostat in order to bring sunlight in here in a steady beam. The lens produces a fixed image of the sun at the point where I'm placing this screen. The mirror on the heliostat is driven by a clock. It rotates about this axis, which we have carefully set parallel to the polar axis of the Earth. The mirror follows the sun. It is set to account for today's elevation of the sun above the horizon in such a way that it reflects rays from the sun parallel to the polar axis of the Earth, regardless of the time of day. Some of the reflected sunlight is intercepted by a fixed mirror behind the window in the periscope tube and is sent down toward another reflection at its lower end, which brings the sunlight into the lab. I had a slit here before. Let me put it back. What we have here now is a prism spectroscope. The continuum is interrupted by many dark lines of varying thickness and intensity. They are all parallel to the slit and signify the absence of slit images over various narrow wavelength bands. This exposure was made on one of the common color films. The eye can see the range indicated. Commercial color films are insensitive to the red above 6,800 angstrom units, but the eye responds to intense light up to 7,600 angstroms. Sunlight, of course, is quite intense. With infrared sensitive color film, the missing visible red portion and even some of the invisible infrared light exposes as red. We are not showing you the remainder of the spectrum below 6,800 angstroms as exposed on this emulsion because it misrepresents the colors in that range. This is a composite of the two exposures. The dark lines in the spectrum of the sun were first studied in detail by Joseph Fraunhofer and are named for him. By his own count, he saw 574 lines between here and here. Our knowledge of this spectrum has been greatly extended since Fraunhofer. Tens of thousands of Fraunhofer lines have been recorded. The most prominent dark lines have been assigned letter names. The study of this spectrum by Fraunhofer was by no means his only scientific work, but it is interesting to note that the more prominent of these lines played a major role in all his other work as reference marks. This outstanding experimental scientist produced the finest quality optical glass the world had seen up to his time. His lenses approached perfection. He put the optical industry on a scientific basis. And, what's more, he constructed the first high-quality diffraction gratings. Fraunhofer's life was spent in or near the city of Munich, in Bavaria. We took a trip there because a number of his original instruments and samples are preserved there, most of them in a large museum of science and technology, the German Museum. This is a sample of glass which Fraunhofer cut from some of his experimental melts. It is actually two samples from two different melts, polished to form a dual prism of common angle. He used it to compare the refractive and dispersive powers of two different glasses. The prism in the middle is made of crown glass. It's light green due to iron impurities, but quite uniform optically and free from internal strains. The two others are flint glass, reddish brown because the red oxide of lead was a major ingredient for this type of optical glass. Flint glass has higher refractive and dispersive power than crown. Fraunhofer modified a surveyor's theodolite into the first precision spectrometer in the history of optics. He focused the telescope on a narrow vertical slit. The slit was very far away. Fraunhofer did not use collimating lenses. When its image was centered on the intersection of the crosshairs in the eyepiece, he read the telescope's angular position on a protractor, which was ruled on a silver circle. It has tarnished over the years. The vernier gave him a least count accuracy of 10 seconds of arc. Next, the prism was placed on the table in front of the telescope. Both the prism and the telescope were turned until one of the dark lines in the solar spectrum was both in minimum deviation and on the crosshairs of the eyepiece. Then the telescope's new angular position could be read on the vernier protractor. From the angle of minimum deviation delta for, say, Fraunhofer line F, he could calculate the index of refraction, N sub F, which his prism has for this radiation, but only if he also knew the value of alpha, the apex angle of his prism. He found this value too by using his telescope in theodolite to the same accuracy with which he knew delta sub F. Next, he measured delta for a number of different Fraunhofer lines using the same prism. Then he went on to do this for other prisms. He charted the refractive and dispersive powers of optical materials. Fraunhofer's personal notes are preserved in the library of the German Museum. On one of the pages, he tabulates refractive indices for a sample of flint, another of crown glass, and for water. Each column cites a value for a given monochromatic light, red at left to blue at right. 6 of the digits are significant figures. He published an important article on the solar spectrum, the dispersion of glass, and achromatic lenses. There's not enough time to describe all the experiments Fraunhofer discusses in his epoch-making paper. Let me just say that his precise values for the dispersion of flint and crown glass led him to design and then to produce achromatic lenses of the highest quality. He changed lens making into a science. He was a gifted draftsman and engraver. The plate from which this picture was struck was engraved by him. For his own use, he watercolored this print. This